So, this is one of our final topics in the big topic we've been looking at recently on vectors, and that's the distance between a point and a line. I'm going to show you what this looks like in terms of a concrete example, but first of all I just wanted you to get a feeling for the type of problem that we're looking at. So this type of problem has a line, which we'll call G in this case, and a point P. And this type of question asks us to find the distance between this point and a line. And I could see you thinking, well, which distance? You know, if G has infinitely many points on it, then of course we could be looking at this distance here, this distance here, this one here, and all of these lines are different lengths. So which one do they mean? Well, the distance between a point and a line, if you're ever asked for this, always means the shortest distance between the point and the line. And the shortest distance between a point and a line is always the one that is perpendicular to the line. So we want this length here, D. So actually, the task here becomes find the distance D which joins the line and the point at right angles. So you're always looking for the perpendicular distance between the point and the line, and hopefully this then gives you some clue about where we might be going with this. So let's look at a concrete example. I've got here a coordinate system. This is the graph that you're asked to look at on page 265, exercise 14.102a. So this is the line G, x plus 2y is equal to 7. And you can see here the 0.51 lies on that line, for example. So we have 5 plus 2 times 1 plus 2 gives us 7. And this would then be true for all of the points on the line. And we have the point P, which is 3, negative 3. So 3 along on the x-axis, negative 3 here. So our point P is here, which is then 3, negative 3. And we want to find this distance here, D, between the point and the line. And we'll do this in a couple of steps. So the first thing we'll do is find the equation of the line that P lies on. And then we'll find where this line crosses G. And finally, we'll find the distance between this point of intersection, so where our perpendicular line crosses G, and the point P. So we have 3 steps. So our first one, find the equation of the line that P lies on. So we want the equation of this line here. You see this dotted line segment? We want the equation of the line that would carry on after this dotted line segment. So we're looking for the equation of this line here. So we want a line that's perpendicular to G and that goes through this point P. So we know about the line that this line is perpendicular to G, which is x plus 2y is equal to 7. We also know this line goes through P, which is at 3, -3. So, what can we say? Well, because this line here is in its implicit form, we know that the vector 1, 2 is perpendicular to G. Because this is in its implicit form, so we can read off a normal vector to this line by the coefficients in front of the x and the y. So we know the vector 1, 2 is a normal vector for this line, so we know the vector 1, 2 is perpendicular to G. So this means this is a direction vector for our new line. And let's give this line a name as we're referring it to it so often, H. This then leads us very nicely into getting a vector equation for the line H. Because for the vector equation for the line H, we need a starting point, and we already know that the line goes through P, so we have a starting point, 3, -3, plus T times the vector 1, 2. And we can check this line with our sketch. So we start here. If I go 1 along and 2 up from my starting point, I end up somewhere else on the line. If I go 1 along and 2 up, I should end up somewhere else on the line. So we have then these points here, which look plausible. Clearly the line that I drew originally was a little bit too rough, but if I join these points together, I'd come out with a line that was perpendicular to G. So this is the equation of the line that I need. And I found that really easily with my direction vector and the point that it starts from. So, the second thing I need to do is find where G and H cross. So, to find where G and H cross, let's just bring the page down a little bit. The point of intersection between G and H is where G is equal to H. So when they have the same coordinates for x and y, then that's the point where they meet. So we have them in two different forms, but that shouldn't be such a big deal. If I rewrite H, instead of using here a big X, what I can say is that this big X represents the point xy, and that's 3 minus 3 plus t times 1, 2. And just to remind ourselves, I'm going to write G here, which was x plus 2y is equal to 7. So instead of writing it in vector form, what I could do is I could multiply this vector and scale it out here and have t times 1 on the top and t times 2 on the bottom. And I could make two equations. So one from the top row and one from the bottom row. So from the top row of H, I would get x is equal to 3 plus t times 1, 1t, which is just t. And from the bottom row of H, I'd get y is equal to minus 3 plus t times 2, or 2t. And now I have separate expressions for x and y. I can substitute each of these expressions into the x and into the y for G. Because I want to find the coordinates that work for both, and so this x and y always works for H for different values of t, and I want to find the time that it works in G. So instead of writing G as x plus 2y equals 7, I can say that g is now 3 plus t instead of the x, plus 2 times minus 3 plus 2t for the y is equal to 7. And then I can multiply this out. So I have 3 plus t minus 6 plus 4t is equal to 7. Then I have 5t, my t plus my 4t. Then I have my 3 minus 6, which is minus 3, is equal to 7. I add 3 to this. I get 5t is equal to 10. Divide by 2. Oh, divide by 5, sorry. Jumping ahead of myself a little bit. Divide by 5 and I get t is equal to 2. Okay, so now if I put t is equal to 2 back into these, I get that x is 3 plus t, 3 plus 2, x is 5, and y is minus 3 plus 2 times 2, so minus 3 plus 4, which is 1. So we have the coordinates 5, 1. And this would also work if we put in 5, 1 here to get 7. And that looks about right on our diagram. I just realised I didn't go up quite enough places. So actually our perpendicular line should be 1, 2, 3, 4. It should be more like this rather than these crosses that I had earlier. I made a little bit of a mistake there, sorry. So our perpendicular line looks more like this, and actually now that looks more perpendicular. So we found our point on the line that P is closest to, and that's 5, 1. So our final thing to do is to find the distance between this point of intersection and the point P. So let's call this point A. Equals A. And I want to find the distance between A and P, which is the same as the length of the line segment AP, which is the same as the absolute value of the vector AP. So AP is P minus A, which is 3, negative 3, take 5, 1, which is then minus 2, 3 take 5 is minus 2, minus 3 take 1 is minus 4. Then the absolute value of this is the square root of minus 2 squared, which is 4, plus minus 4 squared, which is 16. So we get the square root of 20, and that's our final answer. Of course, we can always shorten this answer a little bit and notice that 20 is equal to 4 times 5. And so I have the square root of 4 times the square root of 5, which is 2 times the square root of 5. And so I can simplify my answer in that way. And 2 times the square root of 5 would then be the solution in its smallest possible form. In the next video, we'll practice another one of these with the line in a different form to the one that we had in this one, and so you can see how to do it for different types of line as well.